Okay, so these are the practice problems for lesson 1-2 for Algebra 2 Honors. And right away it says, looks like we've got use this information for items 18 through 22. Some of the water features at Sapphire Island are periodically treated with a chemical that prevents algae growth. The directions for the chemical say to add 16 fluid ounces per 10,000 gallons of water. Okay, so right away, it looks like this is green. Let's change. Oh, what's going on here? We'll change that to yellow, and let's go ahead and highlight this. So we say add 16 fluid ounces per 10,000 gallons of water. Okay. So number 18 says to make a table that shows how much of the chemical to add for water features that hold 10,000, 20,000, 30,000, 40,000, and 50,000 gallons of water. Okay. So I'm going to do this off to the side here. I'm just going to say number 18, and we're going to make a table, and one of the headers of the table is going to be gallons of water. And I'll just put a little line going down here and a line going across. And then on the other side, well, what are we interested in? Well, the fluid ounces of chemical. So fluid ounces of chemical. Okay. Sorry, just adjusting my microphone there. Okay, and anyway, so for gallons of water, we've got 10,000, 20,000, 30,000, 40,000, and 50,000. All right, and they tell us right here, well, for every 10,000 gallons of water, we're going to add 16 fluid ounces of chemical. So right here, first thing, we have 10,000. Well, that would take 16 fluid ounces of chemical, right? Okay, and next up, so we have 20,000. Well, we're just going to double it, right? Another 16. We're not doubling. I guess we are doubling it, but the trend is going up by 10,000, not by doubling. If we were doubling, it would be 10, 20, 40, 80, so on and so forth. This is going up by 10. So this should just go up by 16 every time. So add another 16 here, and we've got 32. We add another 10,000, going from 20 to 30. So add another 16 fluid ounces of chemicals. So that would be 48. Again, add another 16 ounces. That would be 64 ounces. And then add another 16 for 50,000 gallons of water, and that would be 80 fluid ounces of chemical. So there we go. There's our table for number 18. All right, let's go to number 19. Number 19 says write a linear equation in two variables that models the situation. Okay, and it says tell what each variable in the equation represents. Now there are actually a few correct answers to this, and it really all depends on what your scale is as far as what units you're using. In this case, I physically wrote down 10,000, 20,000, 30,000, so on and so forth. One of the options could have been I could have said, well, gallons of water, and I'm talking in 10,000s, right? And I would just put 1, 2, 3, 4, 5, assuming if we're talking in 10,000s, that would be 1 would be 10,000, 2 would be 20,000, so on and so forth. But I'm just leaving these in, just per gallon of water and physically writing out each one of those. And same thing with fluid ounces. So some of you, if you wrote it like this, then really we need to figure out what is the rate of change. You might automatically think it's just 16. So like the answer would be like this, y is equal to 16x. But that's not the case because well, what does x represent here? And we're going to say what they represent, tell what a variable in each equation represents. Well, x is going to end up being the gallons of water, and y is going to be how many fluid ounces. And just to test this out right now, 16 times 10,000 gallons does not get you back to 16, does it? So there's a few different ways we can go about doing this. What I'm going to do is I'm going to calculate the rate of change. And we know how to calculate rate of change. So we'll say rate of change. Rate of change. You guys know this as slope is equal to slope, which is equal to m, right? And we know the equation for m. M is equal to y2 minus y1 all over x2 minus x1. Okay? And again, I'm going to use this knowledge that we already know from Algebra 1 in order to calculate what that rate of change is, because it may not be as obvious as we thought, right? Now, again, I already kind of alluded to the fact that, and in 19 we're going to have to explain that, that x is going to be the gallons of water, and y is going to be the fluid ounces of chemical. So we basically have taken care of that. And you guys know what ordered pairs are as well. If this is x and these are y's, then we could have an ordered pair of 10,000, 16. And the next ordered pair could be 20,000, 32. And all of these could be ordered pairs. And so we could choose any two of these ordered pairs and go ahead and use this this formula here to figure out what the rate of change is. And we're going to do that. And I'm just going to use the first two. So I'm going to say this would be the second one, x1, or I'm sorry, x2, y2. And this one would be the first one, x1, y1. So let's go ahead and plug these in. So for y2, we have 32. So that's equal to 32. For y1, that would be 16. And x2 would be 20,000. And I don't really have room here, so I'm going to put 20k, k representing 1,000, minus x1, which would be 10,000 or 10k. All right, so let's scroll down here. We don't really need that top section anymore. And so we're going to say that is equal to 32 minus 16 is 16, and 20,000 minus 10,000 is 10,000. And when you divide these out, we will just use a decimal form here, and this, we're going to say 0.0016. So this right here, 0.0016, that is actually our rate of change. So we're going to use that in our equation. So again, we're trying to figure out y, which would be the fluid ounces. And that's equal to the rate of change, which is, and actually I probably should have said this to begin with. We're going to be using y is equal to mx plus b. But in this case, b happens to be 0 because b, remember, is our y-intercept, which we're going to answer that in problem number 21. But that's where we start, right? And where do we start with these gallons of water? We're starting at 0. Okay, and how many fluid ounces would you add at 0? Well, 0, right? So B essentially is getting eliminated here. All we have is a linear equation just with a rate of change. So in this case, y is equal to our slope, which is 0.0016 times x. And there you go. That is the equation of our line. Or our linear equation. Now this could actually be different, and again, it really depends on what units you're using. Okay, I'm just using gallons and fluid ounces, so that's what this would be. If you were using something like thousands of gallons, then this would probably change to y is equal to 1.6 times x. All right, so it just really depends on what units you're using. Just make sure that you are clear what you're using, okay? So I've kind of run out of room here, so I'm going to do number 20 over here. All right, and number 20 asks us to graph the equation and be sure to include the titles, a title, and use appropriate scale on each axis. So let's go ahead and I'm going to just go ahead and put in my axes. Might be hard to do. Make them as straight as possible. So this would be X, this would be Y. Let's put in a title here, and I don't know, probably a good title, I don't know, amount of chemical to add, I guess. Amount of chemical to add. Okay. And let's go ahead and provide our scale. Now these, let's see here, whoops. Okay, so again, our X is going to be water, and this is going to be in 10,000s. Okay, so let's go ahead and label that first. We'll say gallons of water. And we have to be very, unless I want to write 10,000, 20,000, 30,000, 40,000, so on and so forth. I don't want to write that out. You could if you have more room. I really don't have a lot of room, so I'm going to say in 10,000s. So that way, when I go 1, 2, 3, 4, 5, why not put a 6 here? This one stands for 10,000, 2, 20,000, 3, 30,000, so on and so forth. Okay, so the Y is a little bit more tricky. This is fluid ounces, and if you look up at our table here, we've got 16, 32, 48, 64, and 80. Now I could kind of like try to use the exact same thing where I would say in 16s, but I mean, our brains don't really work that way. It's usually fine if we go 10s, 20s, hundreds, thousands, 10,000s. That's fine. But, you know, these in between numbers like 16, we usually don't use those. So I'm actually going to go by, I think I'm going to go by 20s in this case. So let's go ahead and do that because we're going up to 80. So I'm going to say 1, 2, 3, and then 4. Okay. And I'm literally going to label this as like 20, 40, just because, you know, over here it's hard to write 10,000, but I can write 20, 40, 60, 80. And this would be 100. All right, and let's not forget to label the side here, which would be fluid ounces of chemical. So we'll say chemical. It's kind of hard to write vertical here, so I'm just going to write chemical, and we'll say fluid ounces. And I'm getting really small there, kind of tough to read. Okay, so I apologize about that, but that says fluid ounces, and this says chemical. A little sloppy there. All right, okay, so let's go ahead and plot our points here. So at 10,000, we had 16 fluid ounces. So let's go ahead and we got 10,000, which is 1, and 16, I don't know, about right here. At 2, we had 32. Let's call it here. 3, we had, what was that, 48? Let's call it here. 4 would be 64, I believe we had. And 5 we had 80. All right, and now it doesn't say to connect the dots or anything like that, so I'm just going to leave it like this. But you can see here that this is a, if you were to connect the dots, this would create a line, and it would actually go through the origin 0, 0, which is everything that we've described so far. And let's go ahead and do number 21. I'm running out of room on this page here. What are the slope and y-intercept of the graph, and what do they represent? Well, slope, we already did this, right? Slope is equal to, what was it? 0.0016, and that is, we'll say the rate of change in, chemical, right? That's what's actually changing here, how much chemical we need to add. And the y-intercept. Y-intercept. I should blow this up a little bit. And then the y-intercept. Maybe this would. I'm learning as we go here. Oop, that thing's floating all over the place. Um, Learning as we go, so maybe this will make it easier for me to make this more legible. All right, so the y-intercept is equal to, now if you were to say the y-intercept is 0, you would be wrong. X-intercepts and y-intercepts, these are points, right? A point is where it intercepts, so it would be at 0, comma 0. And what does this represent? Well, it represents the starting point, right? Starting point with no water. We'll say starting point with no water. Okay, and that's it for 21. And let's go to number 22. Let me zoom out here. So 22 says an employee adds 160 fluid ounces of chemical to a feature that holds 120 gallons of water. Did the employee add the correct amount? Explain. Well, let's see here. So if we have 120,000 gallons of water, why don't we just plug that into our equation and see how many fluid ounces they were supposed to add? And if it was 160, then that would have been correct. If it's not, then then no, they enter or added the wrong amount of water. So let's go ahead and do that. So we'll say number 22. We're going to say y is equal to 0.0016 times 120,000 gallons of water. All right, and we'll say y is equal to, let me grab my calculator real quick, plug that in. And that would be 192 fluid ounces. All right, we'll say 192 fluid ounces of chemical. Which is not how much they how much they added, right? How much did they add? Well, they added 160 fluid ounces, so they were short. So we'll say no. They should have added 192. No, they should have added 192 fluid ounces of chemical. We've come this far, so let's write out the whole thing. Chemical. And let's go ahead and okay. So there we go. All right. Let me zoom out a little bit so we can see the whole thing here. So this is the entire picture of lesson 1-2 practice questions from Algebra 2 Honors.